So something else that we can ask about the universe is, what shape does the universe have? I realize that sounds kind of weird, but remember back to general relativity. Okay, so in general relativity, we talked about how mass bends space. Okay, so if we take the amount of stuff in the entire universe itself might be bent in some way. So that's what we were referring to when we talk about the shape of the universe. Okay, well, the shape of the universe is going to be related to what is known as the total energy density. Okay, so this is how much stuff is actually within the universe. And so depending on the amount of stuff in the universe, okay, then this will cause a bend to the overall shape. So there are actually three possibilities. One possibility is that there is enough stuff, too much stuff in fact, so that the universe kind of curves back on itself. Now the way that we could actually tell this is if two lines that begin as parallel eventually converge. So converge means come together. Now you may be thinking, you remember your geometry, and in geometry it states that two lines that are parallel always remain parallel. That is true on a flat sheet of paper. But if we're dealing with other shapes, that's actually not necessarily true. For example, if you take a round ball, so take the Earth. If you and a friend are standing on the equator of the Earth, both facing north, you are both parallel to each other as you begin to walk north. However, because the Earth is round, as you keep walking north, eventually your paths converge because you're walking on a round ball. All lines that begin parallel facing north at the equator converge at the North Pole because the Earth is a round ball. So if two lines begin parallel and they eventually converge, then this is as if we're dealing with a round ball. So this is sometimes referred to as spherical or closed space. Spherical or closed. Another possibility is if we don't have enough stuff in the universe. In that case, we get the opposite curvature. Instead of parallel lines coming together, we have parallel lines that actually separate. So the lines diverge. So the shape that does this is a hyperboloid. It's this weird kind of saddle shape. So this is referred to as hyperbolic or open space. Hyperbolic or open. The parallel lines eventually diverge. And there's one last possibility. If the energy density of the universe is exactly right, what we refer to as the critical density, then the universe will actually be flat. Lines that begin as parallel will remain parallel forever. Now, what's interesting about flat space is if we live in flat space, so we have a flat universe, then we actually know the amount of stuff in the universe. It has to be the critical density. So to reiterate, if there is too much stuff, if the actual energy density is greater than the critical density, then we live in spherical space. If the actual energy is equal to the critical density, then we live in flat space. And if the energy density is less than the critical, then we live in hyperbolic space. So these are our three possibilities. Well, we can actually test the idea. What we can do is we can look at the oldest light that it is possible for us to see. This is the cosmic microwave background. We'll discuss this more in a little bit. But as we look at the cosmic microwave background, we find that it is not perfectly even. There are some regions that are hotter and some regions that are cooler. The hot spots correspond to regions of high density. The cool spots correspond to regions of lower density. So the hot spots having higher density will actually contract and eventually form into galaxy clusters. The low density cool regions will have material swept out, and those will eventually form into voids. So as we look at the cosmic microwave backgrounds, we actually see the seeds for what is eventually going to become galaxy clusters and voids. Well, we know how big galaxy clusters are today. That means that we can figure out how big those hot spots should be to collapse and form into the galaxy clusters we have now. So as we look at the cosmic microwave background, we can look at how big those hotspots are. And depending on how big those appear, will tell us how the light has moved through the universe. Okay, so for example, if we live in flat space, then parallel lines have always remained parallel, which means that the lines have always gone on pretty well straight paths to us, which means the hot spots will be the exact right size for what we expect to form galaxy clusters in the present day. If, on the other hand, the hot spots are bigger than what is needed to form a galaxy cluster today, that means that the light has been bent. Specifically, it has been bent towards us, which means that we have a magnifying effect and the light has converged, so we have a spherical space. On the other side, if the hot spots are too small, then this means that the light has diverged. We have a minimizing effect, and we therefore live in hyperbolic space. Okay, so based off of these sizes, we can figure out the shape of the universe. And when we have, what we have found is that the universe is flat. Okay, now in some ways that's nice, because if it's flat, then we know exactly what the energy density is, how much stuff is in the universe. We have to have the critical density. But this is also a problem because when we add up everything we know about in the universe, so this includes normal matter, this includes stars, this includes dark matter and interstellar medium and everything, we end up with 32% of the critical density. This means that 68% of the mass energy of the universe is missing. We don't know what this stuff is. Okay, so the 68%, some things that we can say about it. One, it is not luminous. If it was giving off light, it would be obvious. Second, does not have a gravitational influence. If there was this much of it, and it had a gravitational influence, it would again be obvious. Okay, so it does not have a gravitational influence, and it does not give off light. So we don't know exactly what this is, but to help ourselves feel better, we give it a name. We call it dark energy. Okay, we have this dark energy that makes up 68% of the universe. Now, because of the amount of dark energy that is within the universe, we say that the universe is dark energy dominated. Whatever it is that dark energy is doing in the universe will control the eventual fate of the universe.